Welcome to Abstract Synthesis, where we share the stories behind interesting academic papers in the world of program synthesis and neurosymbolic AI. This podcast is brought to you by AGI Research Lab India, and I'm your host, Brian Landers. Welcome, everyone. I'm really excited about today's guest. On previous episodes, we featured Andrew Cropper, my teammate Celine Arquette, and their work on inductive logic programming. Well, both of them were PhD students of today's guest, who actually founded and named the field inductive logic programming, or ILP. So without further ado, welcome to the show. I'm so pleased to have you. Can you please introduce yourself?
My name is Stephen Muggleton, and I'm an Emeritus Professor now since December 2024 from Imperial College, and I've become a Professor of Machine Learning at Nanjing University, where I go for a couple of months every year.
Wonderful. So excited to have you, Stephen. So where are you calling from today? Where in the world are you based?
I'm in London. It's where I spend most of my time, right in the middle of London.
I'm so excited to have you on. Like I said, a lot of connections to our team and advisors to the company, and the work you've done really has influenced the work we do at India on AGI research. So thank you for all that. I'm excited also to dive into a bunch of papers today. Typically, we feed, kind of anchor in one paper, but you've just had such an illustrious career and amazing publishing track record that we have to cover more than one thing. So we'll cover some amazing ground as we talk today. Before we dive into, talking papers and ILP, I'd love to learn just a little bit more about your background and how you got into this space. I know you did a PhD in artificial intelligence at Edinburgh under Donald Michie. I think Michie was among, earliest researchers trying to build systems that could learn from experience rather than being explicitly programmed. Can you tell us more about that experience studying under him?
Yeah, it was a great time. So I joined Donald's research unit in Edinburgh in 1982. But at the time, this is a strange period of the history of AI. AI had effectively been banned in all continents of the world. So as being dangerous or subversive or some such thing, something called the Lighthill Report. And Donald was allowed to keep going, but he was only allowed one student a year. I happened to come across, when I was sitting on a bus going home, as an undergraduate, this leaflet that was sitting beside me that described Donald Michie's setup, and he was talking about the fifth generation project in this leaflet. So I thought, this is what I like. I'm going to go and see if I can talk to this guy. So I went down, knocked on the door, and Donald came out the door, and he said, "Oh, what do you want?" So I said, "Oh, I'm wanting to see if I could do a PhD with you." He said, "Oh, come in." And so we sat around for a while, and he asked me questions, and I explained some things I'd been reading in books about artificial intelligence, and including some of the papers he'd written. And he said, "Oh, that all sounds satisfactory. You seem to be interested." So I said, "Well, what if I started? What would I be doing?" So he said, "Well, we'll give you a topic, and then you'll probably work with some people doing chess, playing chess, and maybe you could do something with that." So I said, "What's the actual topic?" He said, "Oh, it's called induction." So I said, "I haven't heard of that." I went away and read about induction and thought, okay, this sounds kind of interesting. And I read more and more about it, found out it was a term that was introduced by Aristotle, and that it was the opposite of deduction, and there's all this logic stuff and so on. I thought, this is great. I like this, and read more and more about it. I didn't see much of Donald because he was traveling all the time, but I kind of corresponded with him by letter, and I had there were other guys who'd also finishing off PhDs, and so one of them befriended me, or a few of them befriended me. So one of them was Tim, and Tim Niblett. He introduced me to ID3. Told me that if I want to understand it, I better write an ID3 implementation, which I did. It didn't take that long. And then I asked, well, what should I read? And he said, well, there's somebody called Dana Anglin. Read her books, her stuff, and go and read Udi Shapiro's book, which had just come out, about Prolog and how to do inductive inference within Prolog. I thought, oh, it's all been done already. And then realized that there were quite a lot of issues still to be solved.
That is so cool. I'm learning about the origins of ILP here too, which is how you kind of got into it. Mickey, by the way. So I was pronouncing the name wrong. Sorry about that. That's quite the legacy, kind of academic, wise to be a part of, because didn't Mickey study with like Turing himself?
Well, yes. Funny you should say that. He mentioned Turing at various different points, and then he said, oh, he had worked with him. And then I asked how, and he said, oh, because he was at Bletchley Park at the same time.
Oh, interesting.
Much later, he told me that he had worked very closely with Alan Turing and kept, he kept him as a friend even after the war was over. And at a later stage, he said, well, we had to keep everything very, very quiet at that stage, but now we've been allowed to publish what we did. And these two huge volumes came out by Mickey and Good, who were devising this amazing bit of mathematics based on Bayesian probabilities, and all being used in order to infer the content of German messages. And it was just mind-blowing. I mean, he wasn't allowed to say anything up until the year 2000 or something like this.
Wow.
But I kept friends with him then, and found out he did all sorts of things. In fact, when I went along to Bletchley Park and looked at the place, I found hidden behind a screen, there was a picture of Donald Michie in his 20s. He looked unbelievably young. I couldn't imagine him being that young. And it said that he was Turing's boss. He,
What?
as a 20-year-old,
Oh, wow. How did that
had
work?
this guy who's, from the right at the beginning of born at the beginning of the 20th century, and who became this amazing, amazingly well-known person for inventing computers and so on. And Turing and Donald was in charge of him. How he managed to keep Alan Turing under control, I can't imagine.
Yeah. Or like wrangling, maybe. That is wild. What a history. And that it evolved over time. You kind of learned more as you were able to. It's amazing how technology gets built, and the incentives and what drives research,
And the interactions that were going on at the time between Turing, Turing, as you know, probably traveled over and met Claude Shannon, and all these people knew each other. It's quite amazing.
Yeah. So you are a part of that whole, universe, and, connected to sort of modern.
Well, I got to hear the occasional thing here and there where it was allowed.
Yeah. Yeah. That's exciting. I guess, your previous, past, student that you advised, Andrew Cropper, recommended I also ask you about, conversations you've had with John McCarthy, who also, named a field, in his case, artificial intelligence. Just that.
Yeah.
Specifically, around AI and logic, sort of, I guess, like influencing some of your ideas around, ILP. But anything you can share about that?
I think because Donald and John were good friends. I saw John McCarthy quite frequently, and I went from institution to institution. Basically, I started in Edinburgh, and then when Mickey moved across and set up the Turing Institute in Glasgow, I went and moved there. And I remember John came and gave a a Turing lecture. There was a Turing lecture series, so I got a chance to talk to him. At the time, I was making Seigel, and he asked, he's been told that I'm making some machine learning thing with Prolog, and I said, yeah, I'll show you Seigel. And at the end, he said, I didn't think of this. So I've said, no, it's just something I've been trying out. And so he came back several times, and in the end, I went to visit him in Stanford and gave a talk there. And at one point he said, "Well, why don't you come and lecture here?" And I said, "Oh, I'm very busy where I am, so I didn't do that." But he was such fun. In fact, in Oxford, he came down to visit me there, and he stayed in my room and told amazing Irish jokes to me. I mean, I hadn't really thought of the fact that McCarthy is an Irish name, but he's from Northern Ireland. He'd been visiting his relatives there, and then he told me these great, very funny jokes.
That's awesome.
And gave some good talks and stuff as well. So
Oh, that's cool. How very cool.
yeah, and the last time I saw him, he came to Imperial, and I said, "Oh, John, let's go and have something to eat." And we went round the corner, and I said, so it's great to have you here. He said, "Yeah, I'm 80 today." So I said, "This is your 80th birthday. So you should have told me. We could have done something special." He said, "Oh, yeah, well, I just, this is where I want to be."
That's really special.
Very amazing character, really brilliant and great fun.
Thank you for sharing. You mentioned a little bit earlier about, how you kind of stumbled into this, inductive world and inductive logic. But you've been kind of pulling the thread of this, for many decades now. What drew you originally to this space of ILP? It sounds like partly this, study with Mickey, but you stuck around, and what sort of kept you coming back to these problems and revisiting and continuing to write papers?
Well, I got hooked on the idea of machine learning. I thought this was great. I thought it was a good thing to be doing. That I kind of remembered that Mickey had wanted me to do something about induction, and every time I looked at it, it seemed as though it could be done better. It could be more general, and I was frustrated by everybody in machine learning thinking that there was only one way to do things, and particularly since it all just involved propositional logic or variants of it. And I wanted to get something that could at least deal with first-order logic. So I kept on changing, and then found it was really hard to do that. I looked at the way that Gordon Plotkin had tried to do it, and that had limitations. Everything had limitations. So I just kept pursuing different approaches, and eventually ended up with more and more complex things like meta-interpretive logics and all this kind of stuff. But so I think it's just this idea that there was still a lot to do and it was worth doing. And I think, it's a bit like, I don't know if you've ever been to Greenwich in London, but there's this display of the longitude problem where there was a guy who made a clock and said he would beat the Royal Society at being able to tell the right longitude on a ship. And you could see he had 4, 5, 6, 7 different versions of it. And I can kind of get that because you're never quite satisfied. You always think, that could be better.
And that drives you forward. Yeah, I love that. And then, later on you had, students and running a lab and research programs. And so you could kind of scale even those ideas in the work, right?
Yeah, working with students is always great. I mean, because you've got somebody who you can say, look, these are the things that nobody's managed to do, right? Why did you give this a go?
See what happens.
And they always come up with interesting stuff. So, it keeps one alive and keeps one thinking about things, I suppose.
Very cool. All right. Well, I mentioned, we're going to cover, a bit of range and maybe a few papers, but I think it would be really cool to kind of kick things off with, hearing about the very first paper that mentioned inductive logic programming. I think it was named just that. That's the exact title, and it was published in New Generation Computing in 1991. I think maybe it was written in
Yes.
1990 but published in
Yeah.
91. It's a really cool paper, I have to say. As someone not from academia, I found it very exciting. It almost kind of read like a manifesto for ILP. Take us back to that moment where you kind of decided this is when this is all kind of culminating, and I have enough of these ideas put together that I can propose this new framing.
It was, I mean, I think I was both excited about Prolog. I mean, I thought Prolog was an interesting language. Not only was it high level, but you could read it in a declarative way. You could say this is a sentence all on its own, all of these logical sentences, and you can prove things with it. All of that seemed great. I mean, I'm not in any way putting down functional programming. I just thought logic programming is something that I really liked. And I went to various logic programming things, but I also really like machine learning. But it seemed as though nobody was really looking at the intersection of those two, which seemed to be more interesting to me than either of them independently. Okay, so I just thought, look, I've talked to some people, and they seem to think that this is an interesting thing that they're kind of getting into. So I thought, why don't I just come out straight and say, look, we need to look at the intersection of these things, and we need to work together. And I was on a round trip. I was going to Australia, to Sydney, and then I was going to give my first keynote talk, which was in Tokyo at the first algorithmic learning theory conference. And so I thought, this is a good opportunity. And in the title, I'll just say it straight. It's called Inductive Logic Programming, right? It's logic programming, and it's inductive, so it's machine learning. So it's bringing these two things together. And here are some of the things that we need to work on, basically. And the people, I got a lot of positive feedback from that. There were a lot of people who were excited. I'd already talked to Ross Quinlan in Sydney on the way. He seemed to think it was a good idea too. And I was already starting to talk to various postdocs across Europe who'd also were kind of interested in this. And so we went straight on from there to the first Inductive Logic Programming conference in Portugal. Fantastic place, right? I thought, I'm just going to invite everybody along, right, that I know. I invited Stuart Russell. I invited Tony Hoare. I just thought, I'm just going to invite many people here, right? And several of them came, or they sent somebody along because they thought it was interesting. And so it was just a really fun thing to do. And at the end of it, everybody got together and said, we've got to get some funding for this. And so we applied to the European community and were the only one in that year to get funding for machine learning of any kind. So we were machine learning all of a sudden, and we were doing ILP, which nobody ever knew what it was. So until we did it.
That's so surprising. I mean, in today's world, can you imagine? I mean, it's just so much activity happening, and on every side of every field of AI. It's hard to imagine a time where it was so, just infrequent and yeah.
Well, there was a lot happening in logic programming. There was a lot happening in machine learning. We just decided to be at the intersection of the lot happening, which meant that there was a subset of people. And that year we were, I think, the only logic programming, or maybe one of several logic programming, but the only machine learning one that got funded. So they liked what we were saying, and we were very excited about it. So, and then we had 4 or 5 after that follow-up projects from Europe. So it really helped build a kind of community in the European setting. And I was very aware that we shouldn't just be Europeans. We should be having our conference move around the world. So we went to Tokyo, we went to the States. We were going everywhere we could, to Australia and holding conferences there, and everywhere people seem to be interested for some reason.
And they still are. I think Flock is happening in July in Portugal. Coming back there, programming language feature, and it's that every 4 years thing where they combine all the different conferences. Are you speaking there actually? You'd fit right in.
No. Sure. I've given a talk at Flock in the past, but I haven't recently.
They should have you. Maybe it's too late. I'm not sure. I highly recommend you there as a speaker. Hey, you mentioned Ross Quinlan. We'll dive into just what is ILP, inductive logic programming shortly. But can you share any insights about ILP in contrast with decision trees that you maybe gained through conversations with him?
Ross also came across to Mickey's lab and for a fleeting visit, and I got to talk to him a bit there, not very much. But then he sent one of his students over, Ray Buntyne, who was in the middle of doing a PhD. And Ray came to the Turing Institute, and I had a lot of discussions with Ray, and we wrote the cycle paper together. I was just so inspired by the variety of things he said. Like, for instance, he was interested in logic programming. He was interested in machine learning, but he had this other dimension which I didn't really know about, which was Bayesian inference, and that turned out to be his PhD. So I learned a lot about that, and I just thought, these things all go together, right? This really works, right? Because there were various different issues that I couldn't really resolve without involving some degree of probabilistic analysis, right? So how do you do this, right? And there were these things that bugged me, like the learning systems I had, which would add extra learned programs into the program as background knowledge, which could then be used for other things. That all seemed like a good idea until I realized, well, what if they're not quite right? Okay, what if they later turn out to be wrong? Okay.
Yeah.
And it was thinking about Bayesian inference that made me think, no, we got to associate probabilities with these things. They're not just, if we're doing machine learning, they're only true to some degree, right? They're only as good as they are the best, most likely thing to be true, right? We don't actually know what's true. And that way of thinking, which is a kind of Popperian, to my mind, Popperian way of thinking, is a must. It doesn't really come up in machine learning much, because most machine learning stuff doesn't add what it's learned to its background knowledge and then use that to learn other things.
That's right. Yeah.
When you start doing that, you have to have some humility about the truth of what you've added in, right? Because otherwise you're just building bugs on bugs and bugs.
Yep. And not learning from failure. Yeah.
So you need to have some kind of idea of conjectures and refutations and all that kind of stuff that the philosophy of science people have. And I suppose Andrew Cropper's Popper is kind of fits in with that. In fact, one of the people I was very lucky to meet was Donald Gillis, who was one of Popper's students. Karl Popper came over but just before the Second World War, and he spent the war in London. And one of his students was Donald Gillis, who again is a philosopher of science and taught me what I know, the little I know about philosophy of science.
Wow, such wonderful connections.
He had great connections. So he had people who he knew who, like, there was this guy who'd built his own institute after he won a Nobel Prize, and he said, well, do you want to meet this guy? So I said, what does he do? So he said something to do with drug discovery, and so okay, well, and what can I read about it? And he said, well, here's his Nobel Prize paper. So
Mic drop.
Okay, I'll take a look at that. went along to his lab and asked him questions, and he said, "Okay, let me see what you've got." He said, pointed at this one thing on a graph and said, "What the hell is this?" So I said, "I'd have to look that up." So I looked it up in my data, and he said, "That was mine."
Wow.
It's this,
That's so cool.
it's this drug. Its effect is way off the edge of all of the rest. It's a complete outlier. And I thought, that's how you win a Nobel Prize, with outliers.
That's so special. You make the world seem it's smaller. It's just neat to hear the people behind all these amazing ideas. It's just
all
humans
over. Yeah.
doing.
Yeah, exactly. Yeah.
Okay, so inductive logic programming. I think you've actually kind of queued everything up. It's the intersection of logic programming and machine learning. That's very clear. Maybe I guess the other piece is kind of learning like logical hypotheses from examples, and you mentioned background knowledge, which kind of separated it from previous work. And that's, I guess, like, to call it out is very special because the result is highly interpretable, like rule-based models that can learn efficiently from small amounts of data, in contrast to, say, like other machine learning. So these large language models we're all obsessed with take just vast amounts of data to be able to train them. Is that a fair characterization of inductive logic programming? What else should people know? Kind of 101.
No, I think what you've said is spot on. And there are specific issues that came out as things went along. One of them, I realized, I was giving a talk at ICHCAI. I had to give an invited talk at ICHCAI on ILP. And afterwards, I went and met with somebody who I had come across in Denver, who was doing some very interesting work. And David Hausler, he invited me over, and we got into conversation. And I was saying, look, I've been looking at this problem as to how you could learn things without any negative examples, because all of machine learning seems to have negative examples. So, and here I seem to have half of a proof to say that you don't need to do this. So he's quibbled a bit, and I said, yes, I know that, this guy called Gold back in the 1960s shows that proved that this is impossible for everything but very simple regular languages. But there's something that's missing here, and I think it's to do with probabilistic inference. So we worked through the problem I got, and by the end of it, we hadn't sorted it out. And as I was just about to get on the plane, I phoned him up and said, "Yeah, I've got it. I can see what it is." And so there's a paper that came out of that, which is learning from positive examples, which, there were hints of it in stuff that in the machine learning literature, Les Valiant's work. And there was even an example of a kind of setting in which that happened. What I was interested in, isn't it possible with general logic programs to learn from positive examples? And after working it all through and sending it off, I got it published. And yeah, you can learn from positive examples. And I still was bugged much later. Just recently, I then thought, what about one positive example, right? Couldn't you just learn from one positive example? What are the circumstances in which you could do that? And this is the year before last. This is 2022. I'd been involved in trying to organize a meeting at the Royal Society, and we were going to have it in the oldest proceedings in the world. Can you imagine? There's a proceedings that the Royal Society set up, which started at Isaac Newton's time, right?
Wow.
And is still going. So
incredible.
I thought, we want to be in that, right? And I managed to get the proof working just in time and presented it. And I was so pleased, right? I'd missed something in the earlier analysis that you can do under certain circumstances. If your sequence has such a certain degree of very low probability having generated randomly, then you can learn from a single example. You can learn a complete program from a single example.
Wild. That seems like magic.
For that subgroup. It's a very low
For sure.
generality subgroup. But on the other hand, I thought, who cares? Maybe these are the really important things to learn.
Yeah. I mean, it's just also really, it's an elegant, elegant thing to produce. So, it's really interesting to note how you kind of always you're working on these problems, like something that sort of plagued you from a paper years back, and you're kind of still stewing on it and kind of discovering new things, and maybe collaborations kind of kick off new study. But I sort of imagine you on vacation, with a notebook, sort of just quietly working on things.
Yeah, I'm not doing that all the time. Occasionally, I get a bit obsessed with things and then think I'm going to have to break this because I think it's really intriguing and I have to write everything down. And yeah, keeping loads of notes, I think one just has to do that in science anyway.
Yeah, it always results in amazing things. So it's just wonderful. It's like writers who are always kind of working on, a story, and they thought of some theme and it came back in their career later. I get that sense from you. You're very creative.
Well, there's just things that irritate me, and I think that there's got to be some way of doing this.
I love that. Hey, the paper also, Inductive Logic Programming, we were talking about, has a section on real world domains. You spoke about this drug discovery, Nobel Prize winning a thing, but in this case it was qualitative physical modeling, temporal reasoning, which is very interesting, but protein structure prediction, which is related to kind of drug discovery and chemical compounds and that kind of thing. Have those sort of domain picks stayed relevant over time? And also, have other use cases surfaced that are deemed kind of a great fit for ILP?
Okay, so I'm still working in a project at Imperial, even though I'm no longer officially at Imperial. But it was with another of my PhD students, actually the last one, Lunai. So we were looking at something with one of the biology groups, and we ran out of time. And I said, "Well, look, can't we just carry on?" So we're carrying on, irrespective of whether there's funding, and we're close to getting something that we want to submit to a big journal, because it looks like we can do a much bigger version of the robot scientist project that I did with Ross King ages back. The problem is it's such ages back since I did that work that I had to dig around and find out how we actually did it. And Jeff, who's the biologist, keeps on saying, well, he understands all of that, but what about this bit here? Why is this such an efficient way of doing the learning, right? Because what we were doing with Ross back in 2004, we were trying to reconstruct one of the basic amino acid derivation sequence, okay, which you'll find in all modern forms of life, right? All the amino acids that can be generated by your cells, by cells in general. And when we looked at the problem, this is many decades on. I was thinking, but we've got to use this stuff which we've been doing using, Boolean matrices to get really fast convergence analysis of genome level metabolic reactions that are going. Metabolism is, all the transformations that a cell does in order to turn one chemical into another. So I said, Lun, how about using this? And Lun worked on that. We got a paper out of that, but we're now looking at applying it to real data to see whether or not we can do better than the biologists have been doing in understanding and identify errors that have been made. And it turned out again that it's fantastically efficient, right, at converging in. And the only reason is that we were able to do it is that I dug up the code that I'd worked with Chris Bryant, who was a postdoc with me in York. And somehow I'd preserved it somewhere on my laptop, and we went through that, and there it was. It was all this divide and conquer algorithm that we'd figured out that nobody else followed up afterwards. Ross King hasn't followed it up. It was central to what was done with the robot scientist work in 2004, but Ross decided it wasn't interesting. And I've reusing it, and we were getting the effect of months worth of work being done on a normal computer, which is just doing divide and conquer algorithms very efficiently. And it's zooming in on all sorts of stuff. So there's loads of errors that are in there, and we're going to demonstrate those and find revisions, we think, to the existing models of the cell. So yeah, I love that kind of thing. I like working with biologists, and Dave Hausler, who I mentioned earlier, he also likes working with biologists, so much so that he was at the center of the whole genome project in 2001. It was out of his lab that all of the predictions were coming across and being compared with what was going on in Cambridge and so on. I remember writing to him at that time and him saying, "I've got no time. I'm just running after all of this data."
That's exciting. Very cool. Thanks for sharing about the robot scientist project too. That's really, really excellent. Fits in the sort of...
it was a fun project. It was really, really fun project. Really good people that we were working with. I very much enjoyed that.
One more technical question about this first paper mentioning ILP. This section on predicate invention. I think that seems very interesting. It seems to address kind of, one of the hardest learning problems, which is creating new intermediate concepts that are not present in the input, vocabulary, if you will. Do you think, predicate invention could be viewed as an early form of representation learning? Or how do the two concepts differ?
Yeah, I mean, the early work that I did with predicate invention, I think it only went to a very shallow depth. And so being able to decompose a problem in the way that a programmer does, and the way that people like Tony Hoare said, well, this is the way you have to do it, right? I remember having lots of conversations with him because Tony was my boss when I went down to Oxford. And I really didn't have an answer to how we could do that properly. I think now we're narrowing in on this, and the paper that I mentioned to you just recently, I think, gives a way of doing this in a very interesting way to decomposition.
Is it the reduce paper?
It's called reduce. Okay. It's a pun.
Oh, it is? Tell me the pun. I didn't get it.
So because the first system I built was called Deuce, right?
Gotcha.
And it was to do with being the common part of deduce and induce, right? But reduce is going back to deuce. And the key idea about deuce is that you can think of inductive inference. One way of thinking about it is as a compression problem, okay, where you're taking some data and you're squashing it, okay, in a structured way. And what the reduce does is it kind of does in a better way, but has a lot of similarities with deuce. I found after I'd come up with the algorithm that I'd reinvented at least part of it, of what had already been there. But there's a compression algorithm which was made in about 10 years ago, which was based on building a grammar. Okay, so build a grammar from a string. Okay, and you do this by finding the highest frequency sub-sequences, and then you replace those by a definition, okay? And then you you substitute the definition name in, and you keep doing that until you can't do it anymore. Okay, so in the end, you get something that's very compact, and when you look at it, it's got many various different depths of things as it goes down. It's very competitive as a compression algorithm, and you can implement it very quickly, very easily. What it does is it produces something which is lossless. Okay, so you can reproduce the original string, but that's not what I was interested in. I was interested in generalizing the original string, okay, which means making it lossy, but in a very particular lossy way, so that it produces the original string plus lots of other things, other related things. So I put a slight variant of that in, and then connected it up with a representation that I'd been looking at, which is the very bare bones version of a logic program, which is basically, it just shows you how to take a state and transform it into another state by transitivity. Okay, so you just have this one transitivity rule or model, and then you build something that looks a bit like a grammar, but it actually is a general purpose program, so it can reverse a list or whatever you like. And when I got it going at last, I found it was about 1,000 times faster than all of the meta-interpretive learning stuff that I'd been doing before. And I just thought, hey, this is the way to go.
Yeah, it's quite the result.
Wait. This whole problem is NP complete. So I shouldn't be surprised. But if you do this kind of approximation, which is greedy, okay, so you always choose the best choice at every point. You just look at the frequencies and make the best compression at every point. You end up with something very close, and this had already been proved in theoretical papers that I read. It's very close to the optimum. So you're getting NP completeness. This has been the big problem with ILP. It's been the search problem, and I think this is a very competitive approach. I mean, as soon as I tried it, I tried all sorts of things. I was walking through London and I heard Big Ben. And I thought, hey, let's reduce that, and ended up with a program with 33 clauses and sub-definitions for all the bits of the tune.
I love that. I'm a musician, so
it'll go through the sequence starting at 1 o'clock and then go to 2 o'clock and so on.
1,000 times faster and more efficient is just wow. Is that over, outperforming like Deep Log, for instance? That was what the reduced paper was comparing to?
Yeah.
Well, actually, catch us up on Deep Log. What was that, and like what did that demonstrate? Since we just to anchor on what the previous results were.
So I was trying to do something similar with Deep Log, but not using the same technique. So it was still a kind of deep search, but it had a richer representation. And the search was done by basically looking at examples, which are input-out examples, and then identifying a certificate, right? Certificate is a pathway that takes you from a particular state to another state, but you find the shortest pathway. And then you use that shortest pathway and you kind of loop it up into a program. Okay, so the weakness was that it was still non-deterministic. So you could go down different routes, and that was taking more time. So with Deep Log, you could make some interesting decompositions with recursion and so on. Deep Log was used at this Royal Society presentation, and I showed how you could do it using learning from a single example. That was at the center of thing, and you could demonstrate that you could give the problem, and if the certificate had the right properties, you could then learn a whole program. Okay, so I motivated it by saying, okay, suppose I give you an IQ test and I say, let's say Alice is to lowercase Alice, everything's lowercase, is to capital ECILA, as Bert is to what, okay?
Okay.
And the people looking at it, obviously, because it's an IQ test, at least a good number of people will say, oh, it must be capital TREB, because they could see there's some reversal involved. Somebody came up to me and said, oh, they sure that there's some other way of doing it. But I said, oh, fine. Okay, show me. Well, they didn't. And I tried it after because somebody told me about what was happening with all of the large language models. So I thought, okay, give it to a large language model. It completely fluffed it, which was okay. What was surprising then is about 3 weeks later, I tried it again and now it worked.
Now it works. Yeah, the whack-a-mole.
So I thought somebody's taken a look at that paper.
Yeah, maybe even symbolic AI could be something on top, working.
It could be, but to learn from one example and show that it has sufficiently high probability at the end of it for people to agree unanimously in a hall of people that this is the right answer. I mean, it's interesting.
Humans are amazing.
Yeah, humans are amazing, but the mathematics underneath it is interesting too.
Yeah, I mean, this begs the question too. I know we've been talking so deeply with ILP and sort of technical details, but what about ILP in this, and symbolic, machine learning in the world of neural networks, LLMs, like we were just talking about, in this new era? What role do you see ILP playing?
I suppose I became interested in neural networks when I was in Edinburgh. And it was partly because of this mysterious guy who people told me about, who was there just a couple of years ago, all this kind of thing. And I said, oh, so who is this guy? So they said he's somebody called Hinton, right? So he'd just done his PhD. And every so often I took a look at what he was doing and it seemed interesting. And I then read up, where did all these neural net things come from? They came from the time of Turing, okay? And if you look at the very first versions of them, they were propositional logic, okay? All of them could be explained by propositional logic. So the thing that was extra that came in I suppose it's the 80s, was the idea that you could associate all these weights with it and you could then do a kind of back propagation on that and so on. Sounds familiar? Or an inverse of something? Yeah, like inverse logic. But it is inverse logic. The problem with inverse logic, if it's all propositional, is that it is all propositional. The labels that you've got on there, I remember speaking to some of the statisticians about it, Brian Ripley in Oxford, and him saying, oh, they've got it all wrong, it's all weights. What are weights? They should have probabilities there. So I thought about it and eventually thought, yes, it should have probabilities. So I would say it's now called, you should now call it something a bit like statistical ILP, which I think is the right way to do it, right? And it's got the same origins. It's even got the same general methods. I think Jeff Hinton was there the year before I visited Ross Quinlan, and I remember him saying that he thought that things that it should have been done slightly differently, and I agree with him. That what I'm impressed by is the way that he was so persistent in building programs that were decompositional in a setting where you had quite deep networks with probabilities on them. I now think you can do that as well. You can do that using logic, and you can do it efficiently. You can even do it efficiently without using huge amounts of hardware. I think the the marriage to huge amounts of hardware is, to my mind, worrying as an engineer.
Mm.
I
Yeah.
just think, why use all that electricity if you don't need to? I mean, there are efficient algorithms that you can use that would get the same result better, but why are people not doing that? And a lot of the computing industry is simply being driven by hardware, by selling hardware. I think that's a mistake. And I'm sure people will come to the same conclusion at some point, but I just think it's the wrong way around. I think you should be finding good algorithms rather than just selling more hardware.
Yep. Agreed. And just, as you said,
Burning up the Earth's atmosphere.
yeah. I mean, it's sort of it's like they're playing out an experiment of like what will happen if we scale this to the max, and just see what the capabilities are versus like, how do we make it efficient? It will probably come though, don't you think? I mean, those economic issues will drive innovation on the efficiency side. That's a guess.
Yeah, I hope so. But we'll see.
Yeah. What about, you mentioned, I would imagine this is kind of one of the blockers of, more adoption of ILP, is the search, the challenge of search. Do you think there's any opportunity for, LLMs to play a role in making that more efficient?
To making search more efficient?
Yeah.
I think search can be made more efficient simply by using greedy algorithms. I mean, what I was talking about just now, I'm starting to think that's really the way things should go generally. Just use greediness in an effective way. I think in the early days of AI, I remember people just saying, oh, well, you need to have these approximate algorithms that do things, and, you just... It was all kind of, let's do something in a simple way that'll work most of the time. I think properly analyzed greedy algorithms can beat lots of different problems that you would think are intractable. But they do have to be done properly. They don't need, and you need to analyze them properly.
It sounds like a call for research right there. This sounds like a place for people to dig, like see how far greedy search can take you.
I'm kind of surprised that there's so little interaction between the theory people and the let's go out and make a program type people. You don't see that in physics. It's all very tied up. Why aren't computer scientists like that? And you actually use the theory to do what theories are really good at, and particularly with efficiency issues.
I have to say, so, just wrapping up here, but, looking across all your papers, I just want to sort of check this read with you. But to me, it appears like you're kind of, trying to answer this question of like how machines learn structured, human comprehensible knowledge, but use that to make scientific discoveries. The Robot Scientist Project, there's always some like applied part of what you're doing. It's not just theoretical. But does that sort of resonate with you, that sort of read of your overall overarching kind of research trajectory?
I don't think it necessarily needs to it needs to be associated with science. Science has a well-developed philosophy behind it, which is helpful. I think you can apply it in all sorts of areas, in engineering or even in mathematics, or dare I say it, maybe even in the arts. I don't know. I mean, so it just seems to be that there are plenty of opportunities out there to do interesting stuff using AI-type techniques, and hopefully, we're not going to put humans out of business in the process. I think if we do it right, then we'll engage people more in technology, and they'll find it useful and entertaining and productive.
Yeah, that's wonderful. Great message. I hope we don't go back to that dark age of AI being banned, or that seems like not quite the right approach either. Something else.
It was crazy. It was crazy looking back.
It's hard to believe.
Yeah, I know. Well, the debate is all on the web these days, and you can look at what happened, and it's hard to understand now. But lots of people were against it at various different points. And I'm not sure whether it was that they just found it unbelievable, or they thought that it was too expensive, or that it wouldn't work, or what. I just don't understand. But it doesn't look as though it makes sense now, what people were saying then.
Definitely a different world. Yeah. I wanted to ask, is there anything you'd like to drive, attention to? Like, we talked about the reduce paper to, 2025 work. I'm sure you're going to have new papers. So everyone stay tuned for Stephen's new work. Also, I'd call out too, you have some wonderful talks on YouTube. So just publicly available, things that you've presented in the past. Maybe I'll link to a few of those in the show notes, but you can just, search Stephen's name on YouTube and get some great content there. But yeah, what do you, students for programs, is there anything, we can bring attention to while we have everyone here listening?
Yeah, so the paper I mentioned to you, that's coming out as a conference paper. I have a Machine Learning Journal's special issue invitation paper, which hopefully will come out at some stage. They take a little bit longer, but that's been submitted and is under review. Yeah, I'm not quite sure. I mean, there is a bunch, as you say, of stuff on the web. I'm not sure. I haven't looked much back at it much, but you may make some sense out of it.
Yeah, it's great. No, and you're a wonderful speaker. I mean, you can tell you've been a professor. You've got the amazing, engaging way of speaking to people at lectures. So it's a joy to watch. Check out Stephen's work on YouTube. We'll follow new papers. But Stephen, I have to say, you have just such an illustrious career. Your contributions, have been incredible. Like having worked with your past students, a couple generations of them now, including Celine, who's a researcher on our team at India. Thank you. Thank you for all the amazing work you've done and for sharing all that along the way. And it's been, wonderful just getting a chance to speak with you directly. Because I think it was very special. Other people recommending you to come and talk to us on the show here. So can't thank you enough. Really appreciate you joining the podcast.
That's really kind of you. Thank you. Bye.
Thank you, Stephen. All right, and everyone, thank you for watching, and we'll see you next time on Abstract Synthesis.